Hey everyone, and welcome to my channel. Today, we're diving into a fascinating Kaggle competition called CIBMTR Equity in Post-HCT Survival Predictions. We're going to explore a notebook by the great Kaggle Grandmaster AmbrosM. The notebook tackles a really important problem. How can we predict patient survival after a hematopoietic cell transplantation, HCT, fairly across different racial groups? HCT, by the way, is a procedure where a patient receives healthy blood-forming cells, stem cells, to replace their own that have been destroyed by disease or treatment. It's often used for things like leukemia, lymphoma, and other blood disorders. This notebook is all about exploratory data analysis, EDA, and building some survival prediction models. Although I'm not the author, I'll be learning along with you and sharing my insights. Let's jump in. Equity in survival predictions, EDA, which makes sense. The goal here is to make sure our predictions are equitable, meaning they work well for all racial groups, not just one. First up, we see the usual Python library imports for data manipulation, plotting, and some specialized libraries for survival analysis. We also have XGBoost and CatBoost, two popular gradient boosting libraries. Here, the notebook reads in the training data, test data, and a data dictionary. The training data has 59 columns, representing different patient characteristics. Crucially, the test data is missing two columns, EFS and EFS time. These two are our target variables, what we're trying to predict. The data dictionary is super helpful. It describes each of these 59 columns. We've got things like disease risk, psychiatric disturbances, HLA matching, which is about how well the donor and recipient cells match, and a whole lot more. It is good to know the description and possible values of features. Okay, this is where things get interesting. The notebook looks at the distribution of the race group column. We see a pie chart showing 6 different race groups, and they're all equally represented in the training data. This is unusual. In the real world, you wouldn't expect such a perfect balance. The notebook author points out that this means some groups were likely upsampled or downsampled to create this artificial balance for the competition. This highlights the focus on equity. Now let's talk about age. We have two age-related features, donor age and patient age. The donor age histogram looks somewhat normal, but the patient age histogram is very strange. It has these 5 distinct peaks, or modes. This is highly unnatural and is probably an artifact of how the synthetic data was generated for this competition. It is important to be aware of this weirdness. The notebook author digs deeper, plotting the patient age distribution separately for each race group. Surprisingly, all 6 race groups show the same 5-peaked pattern. So, the weird age distribution isn't specific to any one race. Even weirder, the notebook shows that the age of 0.044 years, which is about 16 days old, occurs over 1,000 times in the training data. All other ages occur only a handful of times. This is definitely an anomaly. It makes you wonder why so many patients are recorded as having the transplant at exactly 16 days old. Now let's get to the heart of the matter, the target variables. Remember, we have EFS time, time in months, and EFS, an indicator variable. EFS equals 1 means the patient unfortunately died at that specific EFS time. EFS equals 0 means the patient was still alive at EFS time. This is called censored data. We don't know when those patients eventually died, only that they lived at least that long. This censoring is why we need special survival analysis techniques. We can't just use something like mean squared error, because we don't have the true death time for half the patients. The histogram of the target shows that many patients die within the first 20 months, but those who survive past that point tend to live much longer. Here's where survival analysis gets its name. The notebook plots the survival function, also known as the Kaplan-Meier estimator. This shows the probability of a patient surviving over time. At time 0, 100% are alive. As time goes on, the probability decreases. The key takeaway here is that the survival curves are different for different race groups. Patients with more than one race have the best survival probability, while white patients have the lowest, at least in this dataset. The notebook also shows the cumulative hazard function. This is another way of looking at the same information. It shows the accumulated risk over time. The steeper the curve, the higher the risk. The results of the survival function is consistent with the cumulative hazard function. Now, we move on to modeling. This competition has a special metric that emphasizes equity. The notebook provides a custom implementation to calculate the concordance index, a common survival analysis metric, separately for each race group. The final score is based on both the average concordance index and the variation in concordance index across the groups. Lower variation is better. It means the model is performing similarly well for everyone. The notebook then explores several different modeling approaches. Before diving into specific models, the notebook defines a couple of helper functions: evaluate fold and display overall. These functions are crucial for evaluating the models in a way that's consistent with the competition's focus on equity. Evaluate fold calculates and prints the concordance index for each race group within a single cross-validation fold. It then calculates a fold score that considers both the mean and standard deviation of the concordance indices across the races. Display overall takes the results from all folds, calculates the overall metrics, and presents them in a nicely formatted table. Here, the notebook trains its first model, an XGBoost regressor using the Cox Proportional Hazards objective. This is a classic survival analysis model. The key thing here is how the target variable y is prepared. If f's is 1, event occurred, y is the f's time. If f's is 0, censored, y is the negative of f's time. This negative sign tells XGBoost that the observation is right-censored. The model is then trained using stratified k-fold cross-validation, and the evaluate fold and display overall functions are used to assess its performance. This cell is very similar to the previous one, but it uses CatBoost instead of XGBoost. CatBoost is another gradient boosting library that often performs well, especially with categorical features. It uses the same Cox Proportional Hazards objective and the same trick with the negative f's time for censored data. The hyperparameters are, of course, different reflecting settings that might work well for CatBoost. Now things get a bit more complex. This cell uses XGBoost again, but this time with the accelerated failure time, AFT objective. AFT models are another type of survival model. The way you provide the target data to XGBoost for AFT is different. Instead of a single y vector, you create an XGBoost D matrix and set lower and upper bounds for the survival time. For events, f's equals 1, the lower and upper bounds are both set to f's time. For censored data, f's equals 0, the lower bound is f's time, and the upper bound is set to infinity, np. Inf. This tells the model that the true survival time is somewhere between f's time and infinity. The model predicts the time of death, and it is negated to be used with the evaluate fold function. Similar to the previous cell, this one uses CatBoost to train an AFT model. The target variable y is prepared as a two-column array. The first column is f's time. The second column is f's time if f's is 1 and if f's is 0. Again, this indicates the lower and upper bounds for the survival time. The model predicts log of time of death, and it's also negated. This section explains a key strategy: target transformation. It shows a diagram with a few subplots, showing original target histogram, survival function, and transformed target histogram, to illustrate how different transformations can reshape the target variable to make it more suitable for standard regression models. This part defines several functions: transform survival probability, transform partial hazard, transform separate, transform rank log, transform quantile, that implement different ways of transforming the target variable. These transformations aim to address the issues of censoring and the skewed distribution of survival times. This is a loop that iterates through the 5 different target transformation functions defined earlier. For each transformation, 1. It applies the transformation to the f's time and f's data to create a new target variable. 2. It plots a histogram of this new target variable, showing separate distributions for the event Fs equals 1 and censored Fs equals 0 cases. 3. It trains a standard XGBoost regressor, using mean squared error, not a survival objective, on this transformed target. 4. It evaluates the model using the same cross-validation procedure and custom evaluation functions as before. This allows us to compare how well different target transformations work when combined with a standard regression approach. All right, let's take a closer look at what those target transformation functions are actually doing. We'll examine the histograms they produce, and that'll give us some great insights. First up is transform survival probability. Remember, this one takes the original F's time and converts it to the probability of surviving beyond that time using the Kaplan-Meier estimator. Look at this histogram. See how it's bimodal? We've got two distinct humps. One big one around 0.45 and another, spread out one, ranging from about 0.5 up to 1. What's this telling us? Well, it suggests there are two pretty different groups of patients in our data. One group has a significantly lower survival probability. That's the peak around 0.45. The other group has a wider range of higher survival probabilities. This is important. It even suggests we could maybe treat this, at least partially, like a classification problem. Could we predict whether a patient falls into the low survival or high survival group? Something to think about. Also, notice the imbalance. That peak at 0.45 is much bigger. We'll need to keep that in mind. Next, we have transform partial hazard. This one uses a Cox Proportional Hazards model to calculate something called the partial hazard. Think of it as the relative risk of the event, in this case, death, happening at a particular time, given the patient's characteristics. This histogram is very different. We have a massive spike right at or very close to 0, and then a separate right-skewed distribution stretching out to higher values. This screams zero inflation. It suggests there's likely some separate process that's causing a bunch of patients to have a very, very low hazard. So we might have two distinct populations or two different underlying mechanisms at play. This is going to be tricky for standard regression models. We might need special models designed for zero-inflated data or maybe a two-step approach. First, predict if the hazard is 0, and then, if it's not 0, predict the actual hazard value. This distribution tells that we should probably investigate what features correlate with a zero non-zero hazard. Okay, this one is called transform separate, and it does exactly what it says on the tin. It separates the times for patients who had the event, died, from the times for patients who were censored, still alive at the end of the observation period. It does this in a clever way, shifting and ranking the values. Look at the histogram, it's beautifully separated, two completely distinct, non-overlapping groups. The blue group, censored cases, is clustered on the left, and the orange group, event cases, is on the right. This is fantastic if we want to try a classification approach. A model should have a relatively easy time distinguishing between these two groups, based on the transformed target alone. Of course, this transformed target isn't directly interpretable as a time or probability anymore. It's more like an ordinal rank. Transform rank log is similar to transform separate in that it uses ranking, but it adds a logarithmic transformation at the end. See how we still have two distributions, but they look different now? We have a huge concentration of values near 0, mostly the censored cases. And then the event cases form this right-skewed distribution. The log transform has compressed the larger values. This is a common trick to deal with skewed data and reduce the impact of any extreme outliers. The ranking part means we're focusing more on the relative order of predictions than their absolute values. This plot also shows that there are many values near 0. Finally, we have transform quantile. This one uses a quantile transformation, which is designed to map the data to a uniform distribution. In this specific implementation, it transforms the event times to be uniform, and then puts all the censored times below the minimum of those. And what do we get? Another very bimodal distribution. Even after a quantile transform, we have this sharp peak at -0.3, the censored cases, and a broader, flatter distribution from 0 to 1, the event cases. This reinforces the idea that our original data likely had some very distinct groups or regimes. We're still seeing this bimodality even after a transformation that's supposed to make things uniform. So, we might want to consider further transformations, maybe mixture models, or even that classification regression hybrid approach I mentioned earlier. In summary, these histograms are incredibly valuable. They're telling us a lot about the nature of our data, the challenges we face, and the potential modeling strategies we should consider. They highlight the non-standard distributions, the impact of censoring, and the potential benefits of different transformations. Lastly, the notebook trains a linear Cox Proportional Hazards model using the Lifelines library. This is a more traditional statistical approach, as opposed to the gradient boosting methods. Before training, it uses column transformer to pre-process the data. One-hot encodes the categorical features and imputes missing values using a median strategy. It then fits the Cox pH fitter model and evaluates its performance. Interestingly, with most models, predictions for Asian patients tend to have the highest concordance index, while predictions for white patients have the lowest. The author suggests that a strategy would be to reduce the bias. We can intentionally worsen the result for Asian patients. Finally, we get a nice summary. A horizontal bar chart compares the cross-validation scores of all the models. The transform target models, especially the one using transform quantile, and the Cox Proportional Hazards models perform the best. So that's it for this notebook walkthrough. We've seen how to approach a survival analysis problem with a focus on equity, explored different modeling techniques, and learned about the importance of data exploration and target transformation. Remember, this is just one approach. There's a lot more you could explore, like different models, feature engineering, and hyperparameter tuning. But hopefully, this gives you a good starting point for tackling this challenging and important Kaggle competition. Thanks for watching. If you found this helpful, please like and subscribe for more data science content. See you in the next video.